Hello and welcome to Cardiff Science Festival, or should I say, welcome to the end of Cardiff Science Festival, because I believe I'm the last speaker. So I'm sure you've all had a chance to see loads of these amazing events. I've definitely really enjoyed the festival, and it's definitely an honour to be signing it off. So I'm here today talking to you guys about symmetry. Just a little bit about me. So I'm a doctoral student at the Uni of Glasgow, studying mathematics. So I think about maths for my job. And at the moment, I'm doing my PhD remotely, which is why I'm in Cardiff. But I also did my undergraduate degree in Cardiff. So know it well, and that's why I'm here. So I'm talking today about symmetry, which is pretty much the subject of my PhD. And the title is More Than Just a Pretty Space, How Symmetry Hides in Science. Now, symmetry is an interesting topic for a talk because for different people, there's all kinds of different associations. Now, for most people, when they think of symmetry, they'll be thinking of primary school mathematics. So we learn in primary school that symmetry is when we perform some sort of transformation on an object. We flip it, we rotate it. So, for example, we've got over here these dotted lines reflect it. And we get the same thing again. So we do something to an object and we get the same thing again. We saw that it was quite useful. We could identify different shapes by their symmetry. For example, the difference between a square and a rectangle, or an isosceles triangle and a regular triangle. And then I think for most people, they hadn't thought about symmetry since then. It sort of feels like it's a bit on the back burner, maybe something that we learn in primary school. We're not quite sure what happens with it after that. But actually, I guess I'm here to say that it's very important in science, and it's a huge area of contemporary mathematics. There's still lots that we don't know about symmetry. And that's sort of the subject of this talk. So when I think of symmetry, I think of an area of mathematics called group theory, which is the sort of study of symmetry. So historically, the first people to really study symmetry in a serious way, the first people that sort of dedicated their lives to studying symmetry, would have been Islamic scholars in ancient Iraq in about 825 Common Era. So this would have been the Ottoman Empire. And anyone who knows a little bit about sort of the history of mathematics knows that this is an area where people were, for the first time, really fixing decent notation. So things like the addition sign, the subtraction sign, algebra, Arabic numerals. And these scholars were all based in sort of ancient Iraq. And not just this, but they also were studying symmetry. It was a huge amount of religious importance at the time, viewed as something very pious. And they had made a lot of sort of moves towards things which I think now we maybe take for granted. So they had, for example, defined isosceles triangles, they defined equilateral triangles, regular shapes, these kinds of things. And they'd started to try and sort of classify what different types of symmetries different objects can have. Fast forward to the present day, and modern group theory has all kinds of things going on with it. So yeah, so modern group theory really starts associating to each object a group of its symmetries. So what is a group? A group is just the set of the transformations which leave the object unchanged. So this is sort of, by the mid-19th century, it's really in full force. So Galois had written the sort of first definition of a group as it stands today. And then people went about, so what are the building blocks? What are the smallest groups there are? And those turned out to be called finite simple groups. And they're sort of like the atoms of group theory. So since then, we've managed to classify all finite simple groups. So this is a bit like we've written the periodic table of elements for groups. And this result was an absolutely huge result. So it took over 100 years and the result of more than 10,000 pages of papers. So not one person would know the entire sort of classification. It's sort of like people say it's the first mathematical result, which is like the hive mind of mathematics understands it, but not one single mathematician. And yeah, this is really exceptionally long, probably took the most sort of work of any result in mathematics thus far. And yeah, it was obviously quite complicated questions going on here. So why is this quite complicated? Well, I've got some pictures here that sort of represent a little bit about modern group theory. So in the top right-hand corner, I've got something that is called the first isomorphism theorem, but it's written in a sort of very strange notation, which is called category theory. And since the 19th century, mathematics has changed a lot where it's like grounding is. So at one point it was set theory, then it was category theory. Nowadays, a lot of people work in group theory through the lens of sort of category theory. And so this has made it quite difficult that it's spanned over a period where the culture's changed a lot within mathematics itself. We've also got all kinds of strange objects being discovered. So we've got a Klein surface on the bottom left, which has all kinds of interesting symmetries. It's sort of, yeah, it can be sort of rotated in very peculiar ways. It can be rotated to an irrational angle, unlike sort of other things. And it's also, so we've got here on the bottom right hand side a tesseract, which is an example of a 4-dimensional object. So it's not just considering things like circles, spheres, cubes, but looking at higher dimensions as well. Or even stranger is maybe the top left, which is a sort of surface that evolves throughout time in a sort of discontinuous way. So we get all these kinds of strange objects which we can study their symmetries. And so this is sort of quite a strange thing. So it becomes very hard, even though I think for a lot of people, they think of symmetry as, yeah, the primary school sort of much easier side of things. So just a little bit more on why it's hard. So I feel like that was quite like an abstract example, but I really want to bring it back to home. So let's think about the Rubik's Cube. Okay, so this is something which really relies on symmetry at its core. So we can think of this rotation, all as different types of symmetry. In fact, given a Rubik's Cube, there's only 6 moves that we can do, right? We can go like this, or we can do the centers. And despite this, so I've got this huge number in the bottom left-hand corner, so more than 43 trillion different combinations. So that's enough that given a Rubik's Cube for every different sort of coordination of the colors, we could cover the entire world 275 times over. So we've got 6 possible symmetries with some real sort of rules to them. For example, if I go like this and then go like this, then it's as good as doing nothing. But it gives you all of these different combinations, and it gives you this sort of random, essentially, behavior. When we jumble up a Rubik's Cube, it can be very hard to work out how to solve it. However, group theory really simplifies that task, because it can say, instead of thinking of all of these moves as sort of colors on a cube, we can write equations and stuff which govern it. And this is what is used in, say, like a Rubik's Cube solver on the net, or even what professional Rubik's Cube solvers would sort of do in their competitions. They'd really understand the group theory behind it. Pardon me. So that's a bit about why sort of group theory is hard, and a bit about the sort of mathematics behind group theory, which is obviously my area of expertise. So I'm going to sort of slightly change pace a bit now. So I'm sure you now agree that it's a large part of mathematics. It's what I do for my job and this kind of thing. However, maybe what takes a little bit of convincing is that it's worthwhile. So, you know, it's hard. It's a hard mathematical question. But is it useful? And I think this is actually a misconception. Even within mathematics, people think of group theory as quite a pure mathematics. Oh, sorry. Question here. Is the YouTube chat video visible to the speaker in the audience? Yes, the YouTube chat is. Sorry, where was I? I'll answer questions towards the end. Yeah, I think this is a misconception within the mathematical community that sort of group theory doesn't have a huge amount of applications, and it's actually one of the most applied areas of mathematics as well. And so I just want to sort of talk through some of those things, and I'm going to start with one that's quite abstract, which is in physics. So modern physics has changed quite a lot in the last sort of 100 years or so. We've got non-deterministic systems is a huge change. So we'll have, for example, a system where we aren't sure exactly what the behavior of something is. Instead, we have sort of like probabilities of what the behavior of a certain object is. And this is especially true for very small objects. Hang on a minute. I think I might have frozen. It's okay. I'm just going to assume that everything's working okay. Put my just so you know, I've sort of lost my my monitor, so I can't see the chat anymore. So at the end, I'll have to close it for the organisers. So yeah, but essentially, what we can say about sort of objects is that they have certain symmetries, and the okay, I'm back. Okay. What we can say about an object's behavior is the symmetries behind all the different things that could come out of it. And so I've got an example here, which is the Schrödinger equation. And for those who know what they're looking at, this is essentially like F equals ma for the quantum world. So we have our, over here, this is like the acceleration, this is like the mass, and this is like the force over here. And the theory of Lie groups really simplifies this equation to the point where you wouldn't really be able to get any useful information from this equation without the theory of Lie groups. And so in theoretical physics, it's become a real sort of part of the core, what you need to know. You need to understand groups in order to understand your string theory or your quantum theory, this kind of thing. And it's said that sort of every symmetry corresponds to a conservation law. So in quantum physics, there's all kinds of conservation laws because they aren't as strong as they used to be, I suppose, is the thing. So you, instead of having one sort of very strong conservation law, we often will now have sort of several quite a lot weaker conservation laws. And all of these have some sort of group theoretic underlying. So that was quite abstract, but I would like to move on to chemistry. So chemistry, I think, is a little bit more concrete in terms of symmetry. So a good question is, given a chemical, how do we identify what chemical we have in front of us? So a chemical looks something like this picture over here. And it's quite symmetrical object. You can see that it's got these sort of rotations that we could obviously do to make it symmetrical, and it's got this sort of central point in it. And the group associated to this is called the symmetry point group. And this is one way that we classify molecules, is actually by looking at their symmetries. This is very similar to the sort of way in which we classify different triangles. So we classify equilateral triangles by having more symmetries than isosceles triangles, and similar things. So even molecules that have very similar components or are made out of the same atoms in different configurations can have very different properties. And this is where sort of group theory comes in to sort of help us classify these things. So when it comes to actually applying this, someone will use something that's called an NMR spectrometer. And what this will do was sort of, it stands for nuclear magnetic resonance. So you essentially get this sort of radiation to vibrate the chemical, and the machine will sort of take note of when this chemical is in the same position as it was before, or whether it looks like it's in the same position as it was before. And in doing this, it'll sort of take note of the symmetries, and it'll give you a very accurate reading for what the chemical makeup of a certain compound is. And so this is absolutely essential in modern chemistry. So my partner is a chemist, and she uses a NMR spectrometer like every day. And without it, we wouldn't know what chemicals are in our medicines. We wouldn't be able to safely test water, all of this sort of thing. Underlying it is the science of symmetry. And another thing which I'm sure no one will doubt its importance is the importance of understanding viruses. So specifically viruses like coronavirus, which is pictured here. So viruses have a very strong and very complex geometry, actually. So we have a sort of sphere, the central body, and then attachment proteins, which like these red sticky bits pictured here. And essentially underlying sort of different types of viruses, or corresponding to different sort of attachment proteins coming out, we can imagine that they'll have very different sort of symmetries. But also there's a sort of problem in identifying viruses, which is when we look at viruses under a microscope, we don't get a sort of nice 3D picture like this. We almost get like a shadow of the virus. And so it's quite hard to get a picture of what the actual 3D object looks like. And so this geometrical question is where sort of the group theory comes into it. So the group theory sort of can understand what different projections will look like. And this will help us to sort of identify different viruses, whether someone's got maybe coronavirus or maybe flu, as well as understanding maybe how viruses mutate. So understanding whether we should classify a new variant of coronavirus, for example, because the amount of attachment proteins that we have correspond to, as we say on the slide, transmissibility and half-life. So it's very important characteristics from the perspective of public health and this kind of thing. And so it's quite crucial that we really understand the symmetry of viruses. So I know this is Cardiff Science Festival, but I couldn't resist saying that there's other reasons that people study group theory. It's not just the fact that it's very useful in science. It's also that symmetry is beautiful. And I've put one of the things which I think is the most beautiful sort of tiling system, which is the Penrose tiling for people to see. So yeah, it's not just within science, in chemistry and viruses, in understanding physics. We also have applications of group theory towards architecture, music, art. And this actually led Ian Stewart, who's a very prominent group theorist, to say that group theory is actually the study of beauty, which is a quote that I really, really like. So in art, we see beautiful mandalas to wallpaper patterns on our house. And all of these correspond to groups. In music, the different scales and the different chord structures, again, correspond to groups. In architecture, we have intuitive building designs correspond to different types of symmetries. And all of this comes down to this sort of inherent attraction that a lot of people have towards symmetry. There's a sort of fundamental aesthetic appeal towards symmetry. Yeah. And so now I just want to basically say thank you so much for listening. And I wanted to give some shout outs to some further reading, because I'm hoping that this isn't sort of where people's interest in symmetry starts and ends. And maybe they'd like to read a bit more about it. So the first book that I've got up here is the Ian Stewart, Why Beauty is Truth, The History of Symmetry. And this sort of is an overview of the mathematics behind symmetry, and also the history of sort of people's interest in it. It's a really excellent book and really like beautifully written. For understanding a bit more about the classification of finite simple groups, which is like a very strange achievement in mathematics, a very singular achievement. Richard Ellis has a brilliant expository article right here. And a third one, which is sort of less an academic option, but I still think is like absolutely wonderful, is Beautiful Symmetry, a colouring book about math. So this is like a colouring book where everything that you're colouring in is in some way related to group theory. And so it's an interesting way to learn a little bit about group theory whilst just sort of relaxing and colouring some stuff in. And it's very like nice and mindful. And I've got a couple of shameless plugs. So I've got my blog on the left-hand side and a newspaper piece that I wrote about symmetry for the Glasgow Institute of Science and Technology, which is sort of the newspaper article version of this talk. And yeah, besides that, I just want to say thanks a lot for listening. Thanks to Cardiff Science Festival for hosting the talk. And thanks to Uni of Glasgow for giving me the time to, prepare it. So has anyone got any questions about what I've been talking about? Not sure if I'm not quite getting the... Any questions? Question, why do I like symmetry so much? Okay, sorry if it's coming through a bit late for me. So why do I like symmetry so much? I would say there's a few reasons that I think there's a few reasons that I think I like symmetry a lot. So one reason is that I would say that I find it quite a beautiful thing to be working with. I like that I can sort of think about it. It's quite like abstract, and it takes me into this sort of whole new world where I'm like able to just think about these really abstract things every day. I'm not worried about the news. I'm not worried about that sort of thing. I'm just in this like nice world of mathematics where everyone sort of talks about these things. I'd say the other thing is that it's a decent job to be interested in symmetry. There's sort of a lot of employability within mathematics for it and outside of mathematics. So that's a little bit more of a cynical maybe answer, but it's also, I guess it's true that what influences you as well is sort of the job market and that kind of thing. I'd say, yeah, it's a good question. And I think, the thing is that I also, to an extent, don't know. And this is something about mathematics that is quite strange. A lot of people are just generally interested in mathematics, and they maybe don't know why, or maybe when they get to their sort of undergraduate, they just start being quite attracted towards a certain field and they can't quite put their finger on it. So it's just sort of like a passion of mine. So then I've got another question here by Zaiku Group. Do I think abstract pure math topics such as group theory that are ubiquitous in so many applied topics should be introduced earlier to students, e.g. before university? I think that, truthfully, I think that I'd love to say yes, it should absolutely be introduced to people earlier. But both my parents are teachers. I know how complex writing syllabuses is. And we are taught sort of some fundamentals of symmetry, and we are taught sort of things that go behind groups. So we're taught about algebra and this sort of thing. I think the math syllabus is pretty watertight in our national curriculum. It'd be great if people learnt about, group theory right away. And I think that people would be really interested in it. But they need to have sort of mathematical foundations first. And I think that it's about right how things are. What key things would I recommend to high school students interested in pursuing pure maths at university? What key things? That's a good question. There's a few things that I'd really recommend. So one would be to just do as much maths as possible. So maths is not a spectator sport. Think about mathematical problems, big ones, short ones. Speak to your teachers, because all teachers would just love to hear someone that's thinking about applying into maths and this kind of thing. I would say another thing is maybe to read some sort of science magazines or books. So a really good one would be Quanta magazine. It's a really good outreach thing that's sort of quite accessible for people to understand a little bit about mathematics. And then I'd say as well, get into like puzzles, get into like Sudoku, understanding like all of these sort of newspaper puzzles and stuff that they kind of feel like they're quite good for sort of training your brain towards mathematical thinking, I think. Yeah, I think that's really good. I think I'd especially recommend, so there's a book that I've got up here. Just trying to remember the name of it. I really recommend this book. This is quite a big influence for me. So 101 Puzzles in Thought and Logic. I think that's a really good book for people, because obviously there's a lot of logic underlying mathematics as well as the sort of maths itself. You've got to get used to thinking about things logically and this sort of thing. Any final questions? I know this is the last event of Cardiff Science Festival, so it's okay to keep things going a little bit. But if not, I am always available over email, which you can find through my blog. Thank you. Okay, in which case, thank you very much, and I hope you enjoyed the festival, and goodbye.